So, please get to this page. We're going to continue on. And guys, in the last sort of 3 or 4 minutes, I will give you back your tests and I will email you the solutions. We don't have time to do a post-mortem. Please go home and reflect through the solutions and your test. If you have any issues, you need to come and see me tomorrow or Friday before school, lunchtime, etc., etc. Here's where we got to. Conservation laws apply. Are we good with the aircon? We happy? Yes. All right. That if we're staying inside this gravitational well, this negative potential well that we are trapped in, then we don't really have to worry about negative energy. We can just say that the total energy of a satellite is the sum of kinetic and potential. Uniform circular motion is easy because that is a constant speed, constant radius. Constant speed means that your kinetic energy remains the same. Constant radius means that your height above the Earth, or object that you're orbiting, also remains the same. But not all orbits are perfectly circular. I mentioned this last week, I believe, that most orbits are slightly elliptical. Sometimes you're further away, where you have more potential, less kinetic. You're moving slower. And then there are some times when you're closer. You have less potential because it's been converted to kinetic. So that makes sense. And Kepler used this idea of conservation of energy to figure out equations that we can basically describe the path of any object depending on its ellipse or its orbit. What we tend to do is treat... The great thing is, in one revolution, it all averages out. In one revolution, the radius becomes just the average radius of a circle. And the average speed becomes the average time to do one complete revolution. So that's what we do. We simplify elliptical orbits into circular orbits, and then we can get average velocity, average radius, average period of revolution. Okay? If we want to figure out what the speed is doing at that point in time, then we have to consider converting potential to kinetic and vice versa. This is not in the syllabus, but we understand that the force is not constant. As we leave the object, it drops as per the inverse square law. If we wanted to find the area under that curve, we would integrate. And this is where we got to, I believe. Okay? So we just need to go one little step further. Now, I've discovered that if I sort of tilt like this... No, I'm still going to flip it. Okay, let's pray to the IT gods that this works. Turn. We just want to go one step further. If we set... Where's my Penzies gone? Penzies, where are you? Hello? Hello? Whoa, what's happening? Okay, full screen. What the... I'm scared. All right, here we go. All right. Okay. All right. Purple pen. Okay. We are going to set your initial kinetic energy equal to your potential final, which is 0. And we said that we are in a negative potential well. So I've got to give you that positive number so that you can finally have 0. Basically, we go a half mu squared equals gm me on re. Marcus, what are you doing? That's our potential energy that we need to remove. Not squared. Keep your radical ideas to yourself. We get times both sides by 2 and then take the square root. We get u equals v escape equals square root of 2g me on re. This is the escape velocity for the Earth, mind you. This works for any mass at any distance from it. So let's look at the proportionalities here. The more massive my planet, the greater the gravitational field strength, the deeper the gravitational well of potential energy that I'm trapped in, the faster I would have to leave Earth with kinetic energy equal to potential energy. the further away from the mass, the weaker the gravitational field strength, the further up the side of my gravitational well, the less kinetic energy I need to get that remaining distance, if that makes sense. You can think of it in so many ways. If we doubled our radius, then we've created a scenario where we magically have this potential energy given to us already. So we're already half the way there. Okay, so this is suggesting that there is no energy loss to other forms. There will be air resistance here at Earth. So let's go 40,000 meters above where there is no atmosphere and then fire our rocket thrusters, get us to a V equals root 2 GM R plus 40,000. Boom. That is the required velocity. And the cool thing is, it doesn't matter which way you point. And don't point down because you can smack into the Earth, but you could go horizontal at any angle straight up, you're going to leave. You are going to escape that well. Any additional energy is the fuel that you take with you on your trip. Okay? And it comes out, if you plug and spit all of the numbers from your data sheet into that equation, we get 11,172 meters per second. All right? Ignoring air resistance from the surface of the Earth, that's all you need. It's not much. It's quite easy to do. In fact, we sent 2 objects out of the solar system, in fact, Voyager 1 and Voyager 2 back in the 1980s. And they've only just now recently gone outside of the orbit of Uranus. One of them's gone. I think they're both pretty much never coming back. So we salute them, our little explorers. Now, our waste spec. Let's go back to blue pen. You can get that equation without looking at the integral. So all we do is we go EK initial equals EP final. We'll go a half mu squared equals mgh final. But we do a little side mission and understand that G is not 9.8. That's the value at the surface. We could say that this varies as GME on, or not R, let's call it H squared. Okay? So you get your G, your M, your ME, your HF over your H squared. Cancel-y, cancel-y, cancel, and you get your GME on H. That's equal to that. And so we can still get your U equals square root 2GME on H. It's not in the data sheet, but we can get there. All right? It hasn't appeared recently. It's a little bit tricky. It might, prediction could be in a comprehension section. It's just a slight extension of what you're expected to be able to do. The learning outcomes, time period, velocity of satellites, Kepler's laws, forces, and circular motion. So, it could appear. All right? That's about as much.
Sorry, I just don't quite understand how this actually, is this actually valid? We're cancelling H final with H, which I'm assuming is
H squared.
Is H final the same as H squared?
Yes. Well, no.
This isn't correct, is it? It's just
no.
It's just sort of
it's just a very simple way of comparing kinetic with potential energy.
It's not rigorous in any way.
No. And I doubt that it will appear. And if it did, it would be in the comprehension where it gives you some paragraphs and some equations given that you could then play with. Okay? Yes?
Aren't you unable to use MGH if it's not within a tiny band?
That's why we would go down this path to show this is the correct working out. Okay?
So would you put that in the tip?
Yeah, you can't do that, right?
Not really, no, because it's not quite correct. Now, hold on. Calm down. Shush. Now, we will come back to this page because it's very weird and difficult and hard to explain, but as I said, I put this page in a little bit too early. Really, it should have gone into a couple of lessons later. So let's just get over to my buddy Joseph Louis Lagrange. I believe it should be capital G, Lagrange. Now, here's something fun that we can do, and it has been asked before, and it does appear in a question in the Pearson text and the Heinemann text before we use those. There will be a point somewhere between two masses where the gravitational force of each are equal in magnitude and opposite in direction. Okay? That point is called a Lagrange point. Now, have a quick think. If I gave you two equal masses, that point would be directly in the middle. Because if you are equidistant from them, and equal masses would produce an equal force on you. Okay? But, Malcolm, Edibam, do you need the laptop open? Okay, alright. You can always sit closer if you want. Obviously, the Earth and the Moon are not the same. And so we've got to get a little bit further from the Earth so that its force weakens. We've got to get a little bit closer to the Moon so its force increases, and there will be a point where they equal. Now, we can solve this. The maths is just tricky. And the reason the maths is tricky is because it's r squared. Now, I've set this up. I'm just going to write DS for data sheet. Okay, so we'll go, that's in our data sheet. We've got the mass of each in our data sheet. So we've got all of those values, all right? What we need to set up is a distance from one of the planets, or one of the objects. So I've just said x be the distance from Earth. Then the distance to the Moon is r less x. Happy with that? Okay. Then let's go on a journey. We will say that the magnitude of the Earth's gravitational force will equal the magnitude of the Moon's gravitational force at this point x. Okay? So we can then equate that, putting in Newton's universal gravitational blah blah blah, g m Earth mass over x squared equals g m Moon mass over r take x, all squared. Cancel-y, cancel-y. What can we cancel-y, cancel-y? The mass of the object at the Lagrange point does not factor, nor does g. All right, let's throw all of our masses onto the left-hand side. So I'm going to divide through by the Moon's mass, and then I'm going to put the x's on the other side. Okay? So I've done two steps at once. I divided through by mass Moon, multiplied through by x squared. I will take the square root of both sides, and that leaves us with x on r take x. I will then multiply both sides by r take x. Oh, hang on, I flipped my moons. That would be bad. And what does that leave us with? X. I then might multiply out this bracket to r root me on mm, take x root me on mm equals x. I'm now going to throw my x terms over to the right-hand side. Okay? And then I can factorize a common factor of x. So this is all the maths that needs to be done to get x isolated. It's tricky, but it's doable. Could be one of those discriminator questions in an exam that might separate the 95 percenters from the 85 percenters. If you can do it, you get that extra 5 marks. Lastly, what do we want? We want x equals. Divide both sides. put it in a box. Highlight that box. Now, we're going to play with this number, this value, because it's fun. Get that written down. Actually, does that look good on the screen? No. Get rid of that highlight. Leave it like that. Okay, so we got that all written down. Let's go back to my very simple idea of gentlemen in that back corner and in all other corners and areas that are not corners. Two objects, equal mass. The Lagrange point would be smack bang in the middle, yeah? Well, let's have a look. If I said that ME and MM are the same, then that ratio becomes 1. So X would be R times 1 over 1 plus 1. What's that? R on 2. A half of the radius. A half of the distance between, that is where the Lagrange point is. That would make sense. Here's where it gets a little bit trickier. If we doubled the mass of 1, then is it 2/3 of the way? No, because it's R squared. We're getting, it's compounded a bit by that. You know, you go, if that's root 2, then it's R root 2 over 1 plus root 2. I would just evaluate it as a decimal in terms of X, or sorry, in terms of R, which you could do. Now, let's go back up to the right-hand side. You should have hopefully free. Let's use the values that we know. We've got the Earth. Datasheet says 5.97 by 10 to the 24. And that's center to... We've got the Moon. Datasheet says 7.35 by 10 to the 22. And we're looking for X, knowing that R is 3.84 by 10 to the 8 meters. M. Now, let's just compare the Moon and the mass and the Earth and the mass. You're dealing with 7 compared to 600. The Earth is nearly 100 times more massive. Not quite, but nearly 100 times. 100 is a really nice round number, because if we just went back to this, if the Earth was 10 times more massive than the Moon, 100 times, then what's root of 100? 10. So we get 10R on 10 plus 1, you get 10R on 11. You get that the distance is 10 elevenths the way to the Moon. So it's quite close to the Moon, because the Earth is much, much more massive. You've got to be closer to the Moon so that the forces could balance. So, let's throw the equation in. I've done all the maths to find your Lagrange point. So we'll go X equals 3.84, 10 to the 8. You could just leave it in terms of R if you wanted, and then it would just be a ratio. Root 597, 10 to the 24 over 735, 10 to the 22. And so X, which is our distance measured from Earth, 3.46 by 10 to the 8. Okay? Which, when you compare, is roughly 10 elevenths. Try to draw that again. Roughly 10 elevenths the way to the Moon. Okay? Now this... have we all written that down? Sorry, I'll let you... there we go. We got it all? Yes? Clarky, yes? Can I zoom back up? Aaron, yes? You, yes? All right. So I haven't really drawn this to scale, but our... before the Space Shuttle Atlantis, let's go to the Apollo missions. They chuck them up here, right? When the Space Shuttle takes off, it only needs to have enough fuel to get past this point. Once it gets past that point, it will then fall to the moon. Past this point, the net force points to the moon, and it falls to the moon. Obviously, that rocket gets jettisoned along the way and falls back to Earth, so only that little module falls to the Earth, and then it changes colour for the sake of this diagram. Okay, so the orbiter, and then you've got the Eagle, and the Eagle shot back up and then docked with the orbiter, and then they did what's it called? It's a something burn. It's got a special a Hohmann transfer. It does its burn. It needs to get back to the Earth with these 3 American patriots. Okay. It doesn't need enough fuel to get from there to there. It simply needs to travel. The difference of those numbers, well, it was nothing. The moon's gravity is so weak, it's easy to escape. It literally needed enough fuel to get from there to there. But remember the energy under that curve. So you had all of these engineers in the 1960s, young engineers, fresh from the army, doing the integral from our moon to that Lagrange point using that value. You know, no calculators in that time. They've got all these slide rules and massive whiteboards, figuring out how much energy, right? How much fuel do we need? Let's add a safety factor on in case stuff goes bad. All right, so they only needed enough fuel to get past that point. Then, net force on this side of the Lagrange, net force that way. They fall back to Earth. All right, and then they have the ticker tape parade. So, okay, and then fall. Didn't really need to draw that, but you get the idea. It makes all that sense.
Around that Lagrange point, would there be significant air resistance?
Air resistance?
Yeah.
No, it's a vacuum of space.
How much of a vacuum?
An almost perfect vacuum. In fact, you've given me a brilliant idea. There are some ions. There are charged particles. Yes?
Yes.
If you are in a spaceship or a satellite that's travelling around 10,000 metres per second, then a stationary charged particle relative to you is coming at you at 10,000 metres per second. So they can actually, you get the dosage. How much time do we have left? 6 minutes?
1 mile.
Oh, okay. Here are your tests. I need to stop telling you stupid stories. It's a great story.
Could you tell us why you can test that?
Yes, no, because I got to shout out names, so don't worry.